Welcome friends. So we are discussing network theory. Previously we have solved different network topologies, that is series RL, series RC, series RLC circuit using Laplace transform technique, and we have obtained same expression for current that we have done using differential equation approach. Now in this session we shall solve some numerical problems to demonstrate those illustrations or those theories. So let us demonstrate this problem. We have figure 8 with us, that is we have there is a switch S. There are two positions for those switch. So position 1 is switch 1 and position 2 is switch 2. Now this statement is very important, that is initially that switch S is initially placed at position 1. Now for a long time, because this term is extremely important, for a long time, whenever you come across these phrases, or for a long time, it means it states that the circuit reaches at steady state. So when the circuit that is mentioned in figure 8, it is placed at position 1. So let us say this is position 1 and this is the switch position. So it is placed at position 1 at this position. So this is become switch. So this will be 10 ohm and this will be 5 ohm Henry. Not 5 ohm, it is be 5 Henry inductance should be connected in series with the voltage source of magnitude 25 volt. So it is straight away that under this condition 20 volt source is connected in series with 10 ohm resistance and 5 Henry inductance. Now when that switch is placed at position 1 for a long time, that means it reaches at steady state. Now from the behavior of the inductance is behaving like a short circuit, and inductor should be behaving like a short circuit in case of during steady state. So that will provide a zero impedance path. So this 5 ohm, not 5 ohm, it's 5 Henry inductance will provide zero impedance path. So just before the switching, the current flowing should be is equal to 25 by 10, that will be is equal to 2.5 ampere. Now at this operating condition, another position switch 2, another position of switch 2, it is connected, we have one resistance connected 2 ohm. Now this 2 ohm resistance, it is placed at position 2, and since this position is isolated from the network, so there is no role in 2 ohm resistance when the switch is placed at position 1. Now the switch, now that is the term is said, the switch is placed at position 2 at t is equal to 0. Now this switching has been done. So here it is position 2, we have resistance 2 ohm. Now we have placed the switch is at position 2. So we have 10 ohm resistor and we have 5 Henry inductance. Now the position 1, the voltage source is connected. Now voltage source now kept isolated. Now this part is the active part of the network. Now this part has no connection with the energy source. Okay. So this switching has been done from position 1 to position 2 at t is equal to 0. So at that position, so since switches has been done, so it attains transient state. And since the current flowing through the inductor does not change instantaneously, so we straight away write I0 plus, that will be is equal to I0 minus, which is 2.5 ampere. So that is our initial condition. So now next, for this position we assume any current direction IT. So we write current equation. So first part is 10 IT, that is the voltage drop across the 10 ohm resistor. Then we have 2 IT, voltage drop across 2 ohm resistor, and then 5 DIdt, voltage drop across 5 Henry inductance. That must be equal to 0 because we have no energy source. Now when you apply Laplace transform, then 10 plus 2 becomes 12, so IT becomes IS, so 12 into IS plus, now it will be 5 IT, so if you follow the derivative rule, it should be 5s IS minus 5 into 2.5. That means if you follow 5 into DIdt, so its Laplace transform will be 5 S into IS minus I0 plus. So it will be 5S IS minus 5 into 2.5. Why 2.5? Because I0 plus is 2.5. So that is why it is written here. So IS, now if you solve this, IS will become 12.5 by 5S plus 12. So if you take 5 common, so this will be 12.5 by 5. So ultimately if you simplify, it will become 2.5 by S plus 2.4. So from there directly you can write IT is equal to 2.5 into IT. You can directly write 2.5 into e to the power minus 2.4 t. So that is a solution, current expression for this network when switch is placed at position 2. Now if you observe this expression, so it will follow a decaying exponent curve. So it is quite expected, because since there is no energy source connected at position 2, so whatever energy is stored, that should be dissipated through this resistor. That is why we have this, actually this value, this decaying exponential curve. Okay, so this is IT and this is T. So let us moving towards the next problem. Now it is a two mesh system problems. So first condition is that assume zero initial condition. So let us make the problem very simple. So we have no current through the inductor, and we have also no voltage across the inductor, voltage across the capacitor. So we have assumed two mesh currents. First mesh current is I1T. So this is mesh number 1, and here it is mesh number 2. We have assumed mesh current 2 is I2T. So we need to evaluate the expression. So now when you apply the KVL at mesh 1, so it will be, so KVL at mesh 1, so this is the voltage source 100, that will be equal to 2 into I1 T plus, now 1 Henry means 1 into dI1 dt. Now you see this 2 ohm resistor, the current flowing through is I1 minus I2, because I1 current is flowing from top to bottom in this direction, and I2T current is flowing from bottom to top. So the net current should be I1 minus IT. So we write 2 into I1 minus I2, and that should be equal to 100. Okay, so that is already written. So if you apply Laplace transform of this equation, so 100 becomes 100 by s. It is written 2i1t becomes 2i1s. Now 1 di1 dt becomes si1s minus i10 plus, right? So that if you follow the derivative rule, it should be si1s minus i10 plus, and since we assume 0 initial condition, so this term will be 0. Then coming to this term, it will be 2i1s minus 2i2s, right? So now if you simplify, if you simply simplify, then if you take i1s common, then with i1s we have s plus 4, right? And with i2s we have minus 2, and that should be equal to 100 by s. So that is a equation 1 for us. So moving to our next equation, or next mesh rather, KVL 2, mesh 2, KVL at mesh 2. So what we have here, actually we have again this current is I1 minus I2 flowing through this 2 ohm resistor, so we write 2 into I1 minus I2. Then we have a 2 ohm resistance, the current flowing through this 2 ohm resistance is I2t, so we write that one as 2I2, and the current flowing through the 1 Henry is I2t, so the voltage drop across this will be 1 into di2 dt. So if you follow the polarity, the current flowing through 2 ohm, this 2 ohm resistance is I1 minus I2, so it should be this plus and this minus. Current flowing through 2 ohm resistance from left to right, so this should be plus, this should be minus, and current flowing through the 1 ohm resistance should be this. So if you follow the polarity, then 2 ohm and 1 Henry, the voltage drop across these two elements are additive, so they are added here, and voltage across this 2 ohm resistor will be subtractive with respect to remaining two, so it is written other side of the equation. So now if you apply Laplace transform, then 2i1 minus i2 will become 2i1s minus 2i2s, then 1 di2 dt, it will become si2s minus i20 plus. So from the 0 initial condition we can neglect this term, and the remaining last term is 2i2, so its Laplace transform will be 2i2s. So if you simplify this term, or if you simplify this equation, you will get i1s with minus 2, and with i2s we have s plus 4, that should be equal to 0. So if you arrange them, equation 1, this equation and this equation in a matrix form, we should get s plus 4 minus 2 minus 2 s plus 4, and that should be equal to, that is multiplied with i1s i2s, that should be equal to, now first equation we have right hand side 100 by s, and second equation in the right hand side we have 0, so we should write 0. So these two equation is represented now in the matrix form. Now let us solve I1s first. What is I1s? I1s is nothing but delta 1 by delta. I2s is what? Delta 2 by delta. What is delta? Delta is the determinant of this matrix s plus 4 minus 2 s plus 4, which is equal to s plus 4 whole square minus 4. So it will be nothing but a square plus 8s plus 12. So that is delta. Now what will be delta 1? Delta 1 is the determinant of this matrix. Now this row or this column rather will be substituted by this column. So let us write delta 1, it is 100 by s, determinant of this matrix. So which is equal to 100 by s into s plus 4. So this will be delta 1. What is delta 2? Delta 2 is nothing but determinant of this matrix. Now this time s plus 4 minus 2. Now this column should be substituted by this right hand side. So 100 by s into 100 by s, then 0. So delta 2 becomes 100 by s. So we have evaluated all the terms. So I1, if you substitute delta 1 by delta, so if you substitute I1 delta 1 by delta, I1 s should be delta 1 by delta. So what is delta 1? 100 by s into s plus 4. And what is delta? Delta is nothing but s square plus 8s plus 12. Now s square plus 8s plus 12, if you substitute or if you factorize, then it should be written as s plus 6 plus s plus 12. S plus 6 into s plus 2. So let me check again. So what is delta 1? Delta 1, sorry, I have done one mistake. It should not be, yes, it should be 100 by s. It should be 100 by s into s plus 4. So s plus 4 should be in the numerator. Okay, so it should be in the numerator. So it should be in the numerator. So that is equal to 100 into s plus 4 divided by s into s plus 2 divided into s plus 6. Okay, so let us first solve this. So we have I1s 100 into s plus 4, s into s plus 2 into s plus 6. Yeah. So now let us split it into a partial fraction expansion. It should be a by s plus b by s plus 2 plus c by s plus 6, right? So what will be a? A should be is equal to s into I1 s, s equal to 0. So if you multiply s with I1s, so it will be just 100 into s plus 4 divided by s plus 2 into s plus 6. So if you substitute all s equal to 0, so in the numerator we have 100 into 4 and in the denominator we have 2 into 12, 2 into 6. So it will be 12, 3, so it will be 100 by 3. So the value of a will be 100 by 3. So b, what will be b? B is s plus 2 into I1s. You need to substitute s is equal to minus 2. So let us do that. So if you substitute s plus 2 into I1s, then it should be 100 into s plus 4 divided by s into s plus 6. So let us substitute s is equal to minus 2. So in the numerator we have 4 minus 2, it will be 2. In the denominator we have minus 2 into 4. So we have answer minus 25. We have answer minus 25. And let us solve c. C will be is equal to s plus 6 I1s at s is equal to minus 6. So if you multiply s plus 6 into I1s, so it will become 100 into s plus 4 divided by s into s plus 2. So 100 into, now if you substitute s is equal to minus 6, so in the numerator we have minus 2, in the denominator we have minus 6 into minus 4. So it will be this will be actually minus 25 by 3. So finally we write I1s is equal to a by s. So a we have evaluated 100 by 3. E we have evaluated minus 25, so it will be minus 25 by s plus 2. And C we have evaluated minus 25 by 3 into s plus 6. So from this equation, if we apply the inverse Laplace transform I1t, then the first term will be 100 by 3 only, because it is 100 by 3 into 1. So inverse Laplace transform of 1 by s, that will become 1. From the second term it will be minus 25 is the constant, then it is shifted by an amount of 2, so it should be to the power minus 2t. And from the third term it is minus 25 by 3 is the constant and it is shifted by an amount of 6, so it should be to the power minus 6t. So this becomes your complete expression of I1t. Now similarly if we solve I2t, so here you see this is the solution of I1t. Yes, this is I1t, just we have solved the same result. Now let us solve I2t. What is I2t? Let us first solve I2s. It should be delta 2 by delta. What is delta 2? Delta 2 is nothing but, first it should be 200 by s. It should be 200 by s. And what is delta? Delta is nothing but this, s square plus 8s plus 12, so it will be s plus 2 into s plus 6, so it will be 200 by s into s plus 2 into s plus 6. So we represent this equation as in partial fraction expansion, a by s plus b by s plus 2 plus c by s plus 6. So therefore what will be a? So a will be, it is already done in these 3 steps. Still let us solve one more time. A will be s into I to s at s is equal to 0. So if you multiply s with I to s, so it will become 200 by s plus 2 into s plus 6. So it will become 200 by 2 into 6. So it will be 50 by 3. Here it is your answer. Then we shall solve for b. What will be b? B is equal to s plus 2 into I to s at s is equal to minus 2. So which is equal to 200 by s into s plus 6. So if you substitute s is equal to minus 2, so in the numerator we have 200, then in the denominator we have minus 2 into 4. So it will be minus 25. Here it is your answer. And lastly we have c. What is c? C will be is equal to s plus 6 into I to s at s is equal to minus 6. So this will be 200 by s into s plus 2. So now let us put s is equal to minus 6. So this should be minus 6 into minus 4. So which is will be is equal to 25 by 3. So with that we have I to s, that will be is equal to 50 by 3s 50 by 3s minus 25 by s plus 2, and then final expression 25 by 3 into 1 by s plus 6. So from this we can directly write inverse Laplace transform. Inverse Laplace transform on this equation to write I to t. So first will become 50 by 3, simple. The second will become minus 25 into e to the power minus 2t, because it is shifted by a 2 unit in the Laplace domain. And lastly we have 25 by 3 into e to the power minus 60, because it is shifted by an amount 6 unit in the Laplace domain, so it must be multiplied in the time domain. So we have I to t as solved. It is just as same as that of we have just obtained. So you can see that this partial fraction expansion method is a very powerful method by which you can evaluate inverse Laplace transform quite easily. So this method, that is partial fraction expansion method, is very useful for a function which is fairly complex enough. Okay, so you are required to learn this partial fraction expansion very well. Now just try to draw your attention on this problem, that Now if you want to try this problem using, if you want to try solving this problem using differential equation approach, you will require tremendous time and effort. But you can see that by using Laplace transform approach, we can solve this problem quite easily. So as we have mentioned already, that for a network problem like this, for a complex network like this, where 2, 3 or more number of meshes are there, then this, for this type of problem we have, or if we apply our Laplace transform technique, then it will be quite easier, quite time saver. Okay. So now let us move to our next problem. Now again we have the same kind of figure that we have discussed in the first problem in this session. Now one difference is that again that switch has got two positions, position 1, position 2. Initially switch at position 1 with 10 volt source and 2 ohm resistance, and then this switch is connected at this position, position 1, and this has been done for a long time. Now that position 2 we have connected a capacitor of value 1 farad. Now this capacitor is at position 2. Now this capacitor is isolated from the rest of the network, so there should not be any initial charge across that capacitor. So again you see this language, the switch S is initially placed at position 1 for a long time. So whenever you come across this term for a long time, it means it represents steady state. For a long time means it has reached at steady state. So at steady state inductor behaves like a short circuit, so we can write directly I0 minus, that will also be I0 plus, it should be is equal to 10 by 2, that will be is equal to 5 ampere. So this is the initial condition. Now this is actually now at t is equal to 0. Now that t is equal to 0, we have 10 volt source and 2 ohm resistor. This is position 1. Now at t is equal to 0, the switch now is placed at position 2. The switch is now placed at position 2. 1 farad and 1 Henry, just. So now effectively you see this part actually is totally out. Voltage source and this resistance is totally out. This example is a very excellent example. Through this example you can learn so much, lot of things, right? And now this is position 2, so at position 2 this is made at t is equal to 0. So if you write the KVL equation, so 1 into di dt, then we have a capacitor voltage, so it will be 0 to t I dt, and that must be equal to 0, so no voltage source is there. So we have 1 into SIS minus I0 plus, then we have IS by S, that should be equal to 0. So we have IS common. If we take IS common, then it should be S plus 1 by S, and I0 plus, this is actually 5 ampere. So let us take this 5 ampere at the right hand side. So it will become 5. So IS becomes nothing but 5s over s square plus 1. So now this is a very well known form. You should all have known this form. S by s square plus 1, you know, if you come across this form, it is the Laplace transform of cosine. So you can directly write IT, that will be is equal to 5 into cos t, 5 into cos t. So this is the solution. Now let us try to have some important information from this result. This is a very good, actually very excellent problem through which you can learn lot of things. Number one, so number one observation is that what will be the response of the current at after t is equal to 0. That means when switch is at position 2, switch is at position 2, then what will be the response of the current? So it will simply follow a cosine curve as derived in this fashion. So IT becomes 5 into cos t. So it should behave, or it should follow this cosine curve like this. This is the first observation. It should be plus 5 and it should be minus 5. This is the number one observation. Now, second observation or second question comes, how long it will, the second question comes, how long it will run. How long it will run? It means this response, when this nature, this how long it will run. So the answer is for t is equal to infinity. For t is equal to infinity. Because it is just simple. The answer is quite simple because it will follow the cosine curve. So it will follow this cosine curve for t is equal to infinite amount of time. So with there is no problem with that. A third question is then comes, immediately comes, they are all observation, right? Third question comes, then if this response will run for t is equal to infinite amount of time, then how this is possible? How this is even possible? Why this question comes? Because if you look carefully to this network, you see after t is equal to 0, we have only one inductor and we have only one capacitor. So there is no energy source present. So without any energy source, without being driven by a constant supply, constant energy source, then how it can maintain its curve for a long time? That means if you want to maintain something, you have to have some supply line. Okay, you must have some supply line to maintain something constantly. But here is this, actually it is maintaining as it is, as same as it is, of course, as per this equation, which is the current equation. So it is maintaining this profile for a long time, for t is equal to infinite amount of time, but doubt comes when you see there is no energy source present. So how it is possible? So this is a very third observation, very important observation. How is it possible? The answer to this is actually we have inductor and capacitor. Now inductor, you know, inductor stores energy in the magnetic field and capacitor stores energy in the electrostatic field. Now in the positive cycle, let us consider this positive cycle. This inductor stores energy, and during that positive cycle capacitor discharge, okay. And in the negative cycle, inductor discharge, and that inductor discharging charge will be captured by the capacitor will charge. So in this way, that means in the positive cycle, let us consider inductor will discharge, and where is this discharge charges or energies will going? Capacitor will charge itself using this discharging energy. And in the negative half cycle, this reverse thing will happen. This capacitor will discharge and inductor will charge. So in this way, with the mutual exchange of the energy, this network, this L and C can maintain this profile for a long time, even for t is equal to infinity. Okay. So this is the reason, because for half cycle, positive half cycle, one component will charge, another component will discharge, and in the negative cycle, some other component will discharge and another component will charge. So in this way, this network containing only L and C will maintain this profile in this way. Fourth observation. Now if you go back to our first problem, you have got an expression of this IT is equal to 2.5 e to the power minus. So that is quite obvious. So in this case also, you see, in this case at position 2 there was no voltage source connected. So we are getting an expression like this. Okay. In this case also we have no voltage source connected. So if you keep these two cases side by side, so in that case we have got the current expression as this. So the equation is not important, 2.5 into e to the power minus 4t. Let us consider this type of equation. In the y-axis we have IT, in the x-axis we have time. Now in this case we are getting IT is equal to 5 cos t. So we are getting this curve, and this will be maintained for t is equal to infinity. So both the networks having no energy source, right? Both the networks having no energy source at position 2 at t is equal to 0, but still one is decaying its energy, one curve is decaying its energy in this way and it goes to 0, but another one is maintaining its energy. So what is the difference? Means why this difference? Why it cannot maintain its curve like this? Why it is decaying? Another way, why it is not decaying? Okay, that means this curve, it is curve number 2, why it is not decaying, why it is maintaining same thing? As the why it is maintaining same thing I have already explained, because it is the mutual relation or mutual exchange between mutual exchange of energy between inductor and capacitor. However, but for the curve for point curve of figure 1, it is not keeping that profile as it is following the negative decaying curve. Now what is the reason? The reason is, you see this for this network we have what are the components present. It is present R and L. So whatever is the decaying is done, it is done through this resistance. So resistance is the the reason, because in the figure 1 we have resistance present, and in the figure 2 we have no resistance. So resistance is the element which is responsible for decaying. Resistance is responsible for decaying, or in another word it is said damping. So since there is no resistance, there is no damping. You see, neither increasing nor decreasing. So it is as it is. So it is no damping. Okay. So the resistance is only responsible for decaying or damping out the response. Okay. So that is why we have already mentioned the 3 types of responses. First one is underdamped response like this. Then we have critically damped response like this. Then we have overdamped response like this. And we have also mentioned another type of response. It is called undamped response. Now this is actually the case of undamped response. Why? Because we have no R. We have R is equal to 0. And since in this case, since we have some finite value of R, then we must have some damping, and due to that damping your response is decaying. Like this. Even when we have no energy source for both of the cases, but since there is no resistance present, we have undamped response. So there is no damping in this case. However, for this case, the case number 1, since we have no energy source and still we have a resistance present, so whatever energy stored by the inductor is dissipated through the resistance. That is why it is not maintaining its profile. So we have understood that resistance is the only element which causes damping. So when you come across either underdamped response or critically damped response or overdamped response, you see this means there is a damping is there. So what is the main cause of that damping? It is because of the presence of resistance. And undamped means undamped, there is no damping. So there is no damping means there must not be any resistance present. That is why we have seen this pattern. We have neither increasing nor decreasing. It maintains its profile for t is equal to infinity. So with this problem we have understood few very important observations. So this is a very excellent problem. So with this I am ending here. So application of the Laplace transform, this module 9 ends here. I hope you have enjoyed this session a lot. Just before ending, just quick review between two techniques. First, differential equation approach. Second one is Laplace transform approach. Unless it is mentioned, it is always better to use Laplace transform technique. Now if it is mentioned that for a problem you use this technique to solve, then you have no other options. But if you have a very simple problem, one should use classical approach to save time. But if you have a very complex problem like 2 mesh, 3 mesh system, then you must go for a Laplace transform approach. So with this, I am ending here. From the next session, we shall start our last chapter, which is Fourier series. Thank you.